In this section, we will discuss how threads can interact and coordinate. Coordination occurs through the shared memory model. We will discuss it in detail, and we will also understand some issues that arise from the adoption of the model, and therefore how we need to synchronize the execution of threads to solve these issues. So it's time to get started. In the beginning of this class, we start by discussing processes and threads. Very important, several threads can execute within the same process. And really important for our discussion, this thread share several resources. They share the same address space, they share I/O, they share open files, for example. And this is extremely important. Why? Because the coordination of threads, the way threads interact, is based on shared memory. This is a very important concept, and it's kind of peculiar for threads, and it's different from what you do in distributed application, where some sort of message exchange is always involved when it comes to coordinate among different interactive entities. So in distributed system, you have different processes running possibly in distributed machine or virtual machine, and you exchange messages, for example, through sockets. And this message exchange is the way you coordinate the different components of the distributed system. When it comes to multi-threading, things are different. The coordination of threads occurs by sharing memories, sharing the same address space, and interacting with sharing resources. Very important. This concept is at the core of multi-threading itself. Well, we don't want to get into the detail of the theory of the shared memory model. There are really interesting books on the topic. You can reference one of them. However, we would like just to provide you few basic ideas that may help you in understanding better how to model your software. Basically, when it comes to shared memory model, you have to consider that your application should be organized in terms of active components, and these active components do things. They are the threads, and active components operate on resources. And these resources are shared among them and are allocated in the memory. Resources, the resources that a thread can have access to may be either private. So, for example, a variable that you allocate in your stack, or shared. And shared resources are shared with a multiplicity of threads. In theory, all the threads operating within the same process. And again, I want to repeat it again, in shared memory model, threads interact only through shared resources. The interaction among processes can be either cooperative or sometimes competitive. So threads may compete in order to obtain the possibility to access to a limited number of available resources, computational resources, whatever they are. And in this case, of course, we understand that we should consider some mechanism, tools, strategy, or we want to be able to implement different strategy to rule and organize the way these processes have to interact to have access to available resources. It's clear. We need to control how threads access to resources. In particular, we need mechanisms and tools to define when a given thread is granted the possibility to access a specific resource, and when, meaning under which condition the thread should be enabled, should be granted the possibility to access the resource. This is extremely important as it provides the basis for the definition of resource access strategies that are needed in the implementation of complex multi-threaded applications. Pros and cons of the shared memory model. Well, first of all, clear enough, the interaction among processes is extremely efficient because it is based on a shared memory. So accessing a resource is the only thing you have to do. You have no more overhead. So highly efficient mechanism. The possibility to access a global address space offers a kind of user-friendly programming perspective for developers. I mean, for when you design the business logic of a thread. And another important thing is that you don't need to specify explicitly the communication of data among the operating threads. This is another interesting issue. However, we will get into these details in the following. I can anticipate that shared memory raises issues such as synchronization, memory protection, as you have different active entities operating on the same memory. So you want a mechanism to avoid unwanted and spurious interaction between these entities. Second, programming is significantly more complex as developers are required and are responsible for specifying synchronization policies, the way threads access to shared resources. So let's start analyzing this issue in detail. Let's consider a very simple example. This may guide us and may help us understand something more about the shared memory model and some of the issue we have to consider in order to manage the synchronization among threads. In our example, we have two simple threads, thread 1 and thread 2, and a shared resource. It's simply a list A with 3 elements, 1, 2, 3. Thread 1 and thread 2 both operate on the list, and in particular they update the value of one of the elements in the list. In particular, thread 1 update the second entry in the list, namely A1, and it simply adds A0 to A1. So A1 equal to A0 plus A1. Similarly, A2 updates the value of the third element of the list A2, and its value is equal to A1 plus A2. So something really simple. But, well, it's not that simple. If I ask you what's the result of the execution of this code, it would be very difficult for you to provide me an answer. In fact, you have to concurrent threads, and these concurrent threads are operating on the same resource. And yes, they can interrupt each other. So some operation can be interrupted. They operate at the same time, maybe in a parallel way. And so it is very difficult to tell what's actually going to happen. And the result of the computation is therefore not deterministic. If thread 1 executes before thread 2, we have a result. So the resulting list is 136. On the contrary, if thread 2 executes before thread 1, we have a different result, and A is 135. This is a problem. What we discussed before is known as a race condition. Race condition occur when two or more threads manipulate a shared resource in a concurrent way, and the outcome of the processing depends on the order in which the access takes place. Race conditions make it impossible to predict a priori the processing outcome, and this is a problem when you want to implement software. And as a consequence, it's necessary to provide developers with synchronization mechanisms in order to prevent results that are difficult to predict. In multi-threading parlance, a critical section is a section of code in which threads access the shared resources. To avoid race condition, the execution of critical section, or if you prefer, the access to shared resources, must be mutually exclusive, meaning that one single thread at a time should be enabled to access the resources. This is the only way we have in order to control the outcome of a multi-threading processing. Well, and how can we solve the issue of the critical section? It's necessary, first of all, to define the boundaries of the critical section, and this should be done on a programmatic way. So somehow the developer should define the beginning of the critical section and define the end of the critical section. Then we need some mechanism in order to restrict the access to the critical section to only one thread at any given time. We will see how we can actually solve the critical section issue, and we will start by discussing locks. In this section, we discuss really important topic in multi-threading. We started by introducing the shared memory model. Basically, threads execute in the same process and share several computational resources. And important, they share I/O space and memory. This is really important, as shared memory is the basis of multi-thread coordination, of the coordination among threads. Clear enough, this has impact in software design. First of all, we should organize our code by considering active entities, namely threads, and the resource they access, the shared resource they access. And the access to these resources is challenging. We may have situation where it's impossible to predict the outcome of computation. And this happens when several threads access to the same resource, and the result of computation depends on the order of execution of the threads. So we need mechanisms and tools to rule this situation. These situations are well known and are known as race condition. And really, really important, we have started to understand how to manage this race condition by introducing the concept of critical section. The critical section is the section of code in which a thread accesses a shared resource. And we need tools and mechanisms to define where a critical section begins and where a critical section ends. Plus, we need tools to restrict the access to the critical section to only one thread at any given time. We will understand better how to implement these mechanisms in the following.